Hello everyone, I'm Katrik Sondi, and I would like to thank you for watching a pre-recorded presentation for the ECTC 2020. I'm here to talk about a recent work which concentrates on using a backing layer to increase the flexibility and bendability of passive SMD components on flexible substrates. I have two authors over here, Nathaniel Richards and Saibu Redivatu, both from Jabil, and two other authors, Dr. Zeti Fan and Dr. Nishosri Kaizo Nishida, who are my advisors from University of Florida, with Dr. Nishida being as my main PhD advisor. So now going into the contents. First, I'll be talking about the introduction. Then I'll be going to the background. In the background, I'll be discussing about the processes that were used, the materials that we were using, the testing mechanisms and the testing schemes from which we have done our tests, the modeling basics. In the modeling basics, I'll be giving you a brief introduction about the COMSOL simulations that we have performed. After the introduction background is done, I'll be going into the results and discussion section, in which I'll be talking about the adhesion testing, the bend testing, the backing layer testing, and I'm also talking about the COMSOL simulation. By this, I mean the modeling basics that were discussed earlier. What are the results that we got from all the modelings which were discussed? After all this is done, I'll be going to the conclusion and discussing all the benefits of this study. So now let's go on a journey and let's discuss the effects of backing layer and how this study is very useful for flexible hybrid electronics. Now, before we go into talking about the flexible hybrid electronics or FHE, it's very important to discuss about its predecessor, or I should say its father technology, which is the PCB, printed circuit boards. So printed circuit boards have existed from a long time. PCBs have been used basically for integrating active components such as microprocessors and passive components such as resistors, inductors, and capacitors on a single board, as can be seen over here, and actually here as well. FHE, on the other hand, has been lately being used only for connecting the two rigid PCBs. Now, the PCB industry and the FHE industry is going on different paths. The FHE has evolved itself and is being able to perform more or less the same actions which were possible on a PCB. You can attach SMD components on a flexible substrate. You can make a through hole via on a flexible substrate. Though this existed on Kapton, making it to be called flexible hybrid electronics or flexible electronics, there has been a shift from Kapton to more emerging substrates such as PET. So FHE overall has been gaining a wide interest for the next generation electronics. FHE can, as I said, can now be used for making novel applications such as 3G, 5G antennas and wireless power transfer, which is something that I have also been working on for some time. And so overall, it's an attractive alternative to either replace or add on to the existing PCB technology. In this slide, I wanted to give you a brief background of what we are working on. But before we talk about what we are working on specifically, it is important to understand the parts of what we are working on. So one of the important part is the SMD component type. What you can see in this image is multiple SMD components types. A few of them are such as QFP 20, QFP 44. By the number which you are seeing over here, it just means a different number of pins. Then there are other active components such as SOIC, PLCC, and QFN. There are other passive SMD components also, such as 0805, 0603, 0402, which are very much more smaller and much more easier to handle compared to larger active components, which are being used for microprocessors. Now, once you understood the necessity of these components, it's important to understand the binding agent of these components on these PCB boards. So the solder paste is a very common binding agent. There are other binding agents as well, but that is not the whole scope of this study. The binding agents that we are using is solder paste. And as it can be seen over here, this image gives you a brief idea of how the solder paste looks like, which has been deposited, not before printing, but one which has been deposited, which can be seen over here in these solder pads. So once these components are mounted on these solder pads and the whole stack is reflowed, we get a final stack which looks like this, which has components aligned on those specific spots as needed, and they are not just so easy to break or to delaminate. Now you imagine this whole thing on a flexible substrate as well. So this is an example where I'm trying to show the exact same, I should not say exact, but kind of a similar stack up in which you can see components, traces, as you could see here, the traces, the components, all here on a flexible substrate. Some things which you'll see different are the usage of these encapsulants, the things which are a little bit different over here. The reason why these encapsulants are used, these are basically used to protect them so that when you're bending it, they just don't fall off, the components just don't fall off. So that is the whole goal of our study, to understand methods to reduce the stress so that these components on the flexible substrates can be attached the same way or having the same reliability as they would have one on the PCB. What would this help us? This would help us to make things such as a flexible Arduino, and that is a long, far-fetched project. So once we have discussed the projects and other ideas, now going into more specifics. So for a specific model, we try to go into very basics. And when we're trying to concentrate on the basics, it's essential to understand how can you make up a simple model. So here we have tried to show an example of a very simple model in which we have printed the silver, we have printed the solder paste, we have attached the components and reflowed the whole material stack. So once this is understood, it's important to understand what is the physics behind this. So earlier cases, there used to be a very common equation called Stoney's equation, which was used. And Stoney's equation was used, but it had its own limitations, which were the thickness of the top film was assumed to be very, very less compared to the thickness of the substrate, which is being shown here as a ds. So that is not something which we can use in our study. Something which we can use in our study is to understand the basics of the neutral plane. Neutral plane is essentially the plane of the least stress, and that is shown over here. For an unbent substrate, or I should say a substrate which has not been bent, the neutral axis or the neutral plane is essentially the centroid of the whole stack up. So if you try to imagine a substrate with the substrate components being attached to solder paste, so the centroid or the center of all these materials would help you to understand the neutral plane. When we are bending any material stack, we are essentially shifting the neutral plane. So what would happen? On these pads, the stress would increase or decrease based on the neutral plane shifting towards this or away from this, because there would be a whole gradient of stress created in one direction. So if we try to tackle this point, we will be essentially able to reduce the stress on the solder pads. And what would be the effect of reducing the stress on the solder pads? It would basically be able to reduce, or I should say increase, the adhesion of the components on the flexible substrates. So that is our model of the study. We are basically concentrating on using Young's moduli of substrate and solder balls, which are compatible and can affect the neutral plane shift in a direction which is favorable for us, which is to increase the adhesion or increase the shear strength of components when being bent. Now going into the materials and processes. So the materials which we are using are obviously a solder paste, which I have shown over here. And before I talk about this, it's important to understand that all these properties were calculated in lab. The elastic modulus was calculated using the micro-notation tool, which was also being done using the tool which I'll be talking about the next few slides, which is a map 10. Thickness was calculated using an optical reflectometer. So the silver ink is another thing which we have been using. And I don't want to go into much details of the silver ink and the solder paste which we are using due to proprietary reasons, but it's important to understand that the Young's modulus of the silver ink and the solder paste are widely different. And it is also very important to understand that the silver ink and solder paste are adhered to each other. So when we are bending two materials which have a widely different solder, the Young's modulus, and are being bent, that is, stress is being applied to them, there is bound to happen that there will be some amount of cracks. So the whole goal would be to overcome the stress and to increase the adhesion. Coming back to this slide, the fabrication processes that we are using are screen printing and stencil printing. They're essentially the same. The only difference is that in screen printing, you are having a screen, which is basically a mesh. In our case, it's a 325 stainless steel mesh. And in a stencil, we have a stainless steel frame which has patterns which are through cut. So in any screen printing or a stencil printing process, we have a squeegee. The squeegee presses on the screen or the stencil with its impression on the screen or stencil, and keeping a constant speed of the squeegee, we are able to deposit some amount of patterns on the substrate, which is being shown through this color. And there's a base plate at the bottom. At the end of the process, the squeegee either has a print flood or a print mode or a flood print mode, and the patterns are basically deposited on the substrate. In this slide, I'm talking about the possible bond testing schemes. So now there are different bond testing schemes which are available. One of them is the ASTM F1269, which talks about the shear test. The second one is an IEEE standard, which is a pull test. Now, each and every standard has its own description and its own basics, but the whole goal of understanding or using these standards is basically to understand the shear strength of the components when on a specific substrate and when they're trying to be delaminated from a specific substrate or a specific stack. So if we pay attention to this instrument image which I'm showing over here, the shearing ram or the shearing ram as can be seen over here and can be seen over here, basically what it is trying to do is it is trying to delaminate the component from the PCB. A kind of a similar thing is happening here as well, but the basic difference in this case and in this case is that in the pull test case, it is trying to pull it from the substrate. But in this case, which is a shear test, it is trying to shear it off on the surface. So both these tests are a good or provide a good understanding of the adhesion of the component to the substrate, but they have quite different criteria. And the values which you will be getting are also different. So if you try to calculate the shear strength of a component to a shear test, the F value or the shear strength value will be particular for the shear test only. So these are the basic differences of the tests which are being used in and around us for testing the addition of components. And we are only going to talk about here the shear test. So in this slide, I'm basically talking about the initial component shear testing. And please don't mind the video. I'm basically here showing you how the component is being sheared in our study. So if you pay attention to the 14-pin TSSOP component, what you'll see is a component which is being sheared off from the PCB board. This is an output graph which we get using our tool for a fixed strain rate. Now this is very important to notice because the shear strength or the force which you'll be observing for a particular graph will or may vary based on the shear strength, the strain rate. In this case, we are trying to shear off a 5mm pin, 14-pin SSOP component. And another thing which is very important to note is the interaction area between the tip and the component. Now going into the process flow and the shear testing. So for the process flow, now this process flow is not specific to our process. I also wanted to give you a brief background on the processes which are used for flexible hybrid electronics. In the case of flexible hybrid electronics, so this is an example of a screen printer. Now all the screen printers don't look like this. This is one of the automated screen printers which we have in our lab. So we are printing with screen printing with the DEC Horizon 03i. Once one round of silver printing is done, the silver is cured. After the curing of silver, we print the solder using the stencil. Once the solder has been printed, we are mounting the components on the uncured solder or the unreflowed solder. Once the whole components have been now mounted, they are again reflowed in an hour, and finally we are evaluating the shear strength. So this basically is all these things. The shear strength evaluation is done using an equipment called Mark 10, which looks like this. So for doing this, we have an ESM303, which is a motorized test stand, which is controlled using a MATLAB instrument control toolbox using the codes which I have written. It has an integrated force gauge. It also has G1062 clamps. The standards which we are following specific to the study are the bend test, ASTM F2749, and the shearing test, which is ASTM1F1269, which I've already discussed. And the only outputs which this study gives is force and the displacement of the clamp. So this is very important to understand, because this equipment does not give you the shear strength of the component. It basically gives you the force, and from the force we have to understand the shear strength of the component. Now going to the COMSOL simulation. Now once we have discussed the experimental model and how we are doing the tests and what are the basics of all the tests that we are doing, it's understand and replicate the exact same model into COMSOL. So this is something which we have actually put a lot of time in. And the first step of using or defining the COMSOL model is to understand or define the geometry. So as you can see over here, our model is actually very, very detailed. And it also takes into account the air which is between the component, in this case, 2-pin SMD component 1206 or 0805. We are basically showing the distance between the component and the substrate is also being used. We are also showing the backing layer, the silver, the component, the substrate, and all these things makes the geometry. Once the geometry is defined, it is important to define the specific materials and the material properties. So for this, we have used all the materials specific to the 1206 or 0805 component. In this case, we have simulated or added the materials for the edges of the SMD component, which is alumina, copper for the inner lining, the silver for the silver which we have printed, the air which, as I had already discussed, solder paste which is printed, the polyethylene which is the substrate, PDMS which is the back layer. Once all this is done, we use the relevant physics. An obvious choice to use a physics which will help you to understand the stress is the structural mechanics. In this case, we have used different subsections of the structural mechanics which I'm showing over here. The different boundary conditions are also shown over here. We also use the heat transfer module. So the heat transfer module is just used to understand the post-reflow condition and to simulate first the post-reflow and then going into the stress which will be occurring during the bending. So now, once that COMSOL is defined, now I'm going into the results and discussion section, which also includes the fabrication process. Understanding this is also very important, because understanding the reflow curve helps you to get an idea of how and why this whole process was done. So at first, we use a spin-coated PET. The spin coating of PDMS on the PET was done also in the lab and was done for different thicknesses and different times of PDMS, or spin coating time. After the spin coating of PDMS was done on the PET, we have then printed the silver. Once the silver printing is done, the solder printing is done on the exact same place. The components are mounted and the whole stack up is then reflow. Once this is done, it is also very important to understand the reflow time. So this time, which is being shown over here, is the N, or the maximum reflow time, was modified and was optimized for our specific process. So the whole reflow conditions have already been optimized. So all the results which you have been seeing from now are for the optimized conditions of the reflow time. So now we'll be discussing about the substrates and component bending study. In this slide, so I'll be talking about the component shear strength, which is a function of the component sort of adhesion, the strain rate, and the external stresses being experienced on the substrate surface. I'm using the word surface, but technically or theoretically, it is all the interfaces, which is the component solder, the solder substrate, the silver substrate, and all these interfaces. In this graph, I'm showing basically two stresses. When I'm using the word stresses, I want to say two variables which are applying stress on the component. One of them is the thickness of the substrate, something which can be seen that thicker the substrate, higher is the external stress being applied on the substrate. This could also be understood when we use the Stoney's equation. Secondly, I'm showing and talking about the effect of the bending. The reason why this is important is because we also want to understand how the bending of component affects the shear strength of the component. And this is the whole goal of using FHE. So one thing which can be seen is that for 1 by 2 millimeter of bending radii, the component shear strength is very, very low. The maximum component shear strength is obviously seen when the component is not bent. The nice thing is that if you would repeat these studies for PCB, the component was definitely delaminated. But in our case, all these components even have a 2.5 millimeter bending radius. Now this is all without any backing layer. Now going into the next slide, we start talking about the backing layer. Now as I already discussed earlier, the PDMS was spin coated for different thicknesses by using different spin coating time and different spin coating speeds. So once all the processes are done with the PDMS on the back, we can see that the component shear strength is changing. And this is for no bending condition. The reason why this is important is because in this graph we had seen bending condition. Now we go into the no bending condition. Something which can be seen is that the component shear strength increases for up to a fixed PDMS thickness, which is different for different thicknesses of the PET. So when I'm saying 178 micron, again, it is the 178 micron is the thickness of the PET, and 254 micron is the thickness of the PET, another thickness of PET. So something which can be seen, the optimal thicknesses for both these conditions varies, and this is all based on the shift or the position of the neutral plane. Something which can be seen is earlier we had the maximum shear strength of the component around 1.75. That has doubled for 178 micron, and similarly when we had the 254 micron PET substrate, the component shear strength also doubled. So the maximum shear force has doubled for both the cases. And this is because in these cases, the shift of the neutral plane is towards the component interface, which effectively causes a lower reduction in the stress. The standard deviation of the shear strength could be because of multiple reasons. One of them could be the non-uniformities of the PDMS adhesion. By that I mean, even though the PDMS is spin coated, it is very easy to delaminate because it is not made for adhering to PET. So these are some things which can be worked on and can be developed. Finally, going into the COMSOL simulations and the results which we are getting. After observing all the experimental results, it's important to also visualize the COMSOL results. So results which I'm showing on the right hand side show you the stress on the solder pad. The same thing which you had seen in this slide. So try to imagine this cross section. This is the cross section which we are showing over here. So when you look at this cross section and look at the color part, something which can be observed is for the optimal thickness for PET 170 of thickness of 175 micron, we observed that the stress was the least on the solder pad. And this is the whole goal of what we're trying to talk about. Now these results can also be observed analytically. So these two graphs are actually from MATLAB, in which we have shown or tried to simulate the effect of the stress based on the strain conditions. And these strain conditions give you a provided estimate of the values which are based on the material layers and the position of the neutral plane. This also provides an insight into the thickness, which would pose the least stress conditions. Finally, the stress on the solder pads, as I said, can be seen on the right hand side. Now going into the conclusion and summarizing my whole presentation. So we have used 2 different substrate thicknesses and 6 different backing layer thicknesses to show you what an optimal backing layer thickness can be. This study also provides an insight to the condition that an optimal thickness can be obtained for reducing the stress on the solder paste or the component so that the component can be bent more easily. We have also used COMSOL, which is a very cool thing to simulate the stress and predict the stress which could happen for a particular condition. So if we're using this kind of pre-evaluation technique, we need not actually fabricate the sample, but just test it on COMSOL or MATLAB and then think about fabrication of the sample. Additional benefits of this technology is that this is a kind of a universal model. This can tomorrow, if I would want to change PDMS to another substrate, say I want to use a backing layer which is a tape or a double-sided tape, I can even use a double-sided tape and get the exact same conditions. So that's why this model is very universal. Finally, going into acknowledgements, our sponsors are the MIS Center and the NSF. The places where I've worked are the UF RSC, or the Research Service Center, which is NRF, and IMG, which is a group I belong to. And this is the Nishi Recruitment Fan Group, which I would definitely like to thank. Finally, I'm welcoming you to read our proceedings paper and follow our studies, which we publish on component attachment and other sections of flexible hybrid electronics. Thank you.